In this lecture, we are going to analyze heat conduction by using partial differential equation and its solutions. Let's first look at the figure in the center. If there is a piece of glass, separate the space inside the house and outside the house. And if the glass has a thickness L, then the hot air, the temperature will cause the heat transfer from high temperature to low temperature. And the heat transfer through the glass is considered a molecular motion, collisions caused by molecules, atoms, and electrons. And outside the house, there are some air circulation. The air circulation will move the heat away. It's through the bulk motion of a collection of mass. So these are the two different heat transfer mechanisms in two different regions. And there is a third heat transfer mechanism called radiation. Radiation is caused by, for example, the sun radiates its energy without any medium. It can transmit the heat from high temperature to low temperature. All these heat transfer mechanisms should be discussed in other courses you are taking. Here in this chapter, we focus on heat conduction, particularly in solid. This system, heat transfer inside the glass or a piece of metal, can be analyzed by energy balance. If we take a energy balance, we shall be able to obtain a partial differential equation like this. Notice this is a second order partial differential equation because the highest derivative in the equation is second order. And what is the difference between this heat conduction equation and the stream vibration equation is the left-hand side is only the first order derivative of temperature with respect to time. In stream vibration, we have second order derivative on the left-hand side. And on the right-hand side, very similar to the stream vibration, we have a parameter. We designate it as C squared. It's related to the material. We will discuss briefly shortly. And this partial differential equation is also linear. If it's linear, yes, we can use the method of separation variable to solve and find a series solution associated with this differential equation. And the solution temperature is going to be a function of both position and the time. In the subsequent discussion, to be uniform in the discussion, we are going to use U instead of T to designate the temperature to be uniform for this chapter. We are going to designate the dependent variable as U rather than temperature. In this steady state, this particular problem inside the object, if we have constant heat transfer from the house to outside the room, then the left-hand side is going to be 0. So the solution of an ordinary differential equation of second order is going to be, it's going to have a linear solution like it's represented here. And in order to find the solution of the equation, we look at it, we have to make certain assumptions. The assumption number 1, the specific heat and the density of the material remains constant, and the heat is provided or disappear inside the object. Second, this is called Fourier heat conduction law. The heat flux, that means energy passing through a cross-sectional area per unit time, is proportional to the temperature derivative. Temperature derivative with respect to distance. And this K is called thermal conductivity. As you can tell, when the temperature gradient is high, the heat flux will be high. And this thermal conductivity also depends on the material. We can imagine for glass, the heat conductivity will be relatively low. If we are talking about heat transfer in copper, the heat conductivity will be very high. We can sense the temperature rise if you heat it up. If we heat up an object, we can feel the heat on the other side very quickly. And these are the basic assumptions. And if the author of the textbook did derive a PDE through these assumptions. This is the PDE we get, and second order linear ODE. C squared is a parameter corresponding to thermal conductivity divided by density times specific heat. Also called heat equation. But I have to emphasize it's specifically for heat conduction. If we have a 3-dimensional object, this equation can be expanded as this. So that means we can heat up, we can deal with this equation that involves heat transfer in a 3-dimensional object, not only 1-dimensional, 2-dimensional, 3-dimensional. That makes this equation highly versatile. This equation can also be used to analyze the diffusion phenomena, because diffusion and the thermal conductivity are based on the same molecular motion inside the material. For example, if someone dumps a bucket of chemical in a lake, and we can analyze how fast these pollutants will be transferred in the lake. How fast, in terms of the position and the time, essentially that is the same equation, because we can take material balance based on the very similar assumptions, and we can generate same equation. So be aware this equation can be analyzed by for the mass transfer problems. Also, let me make another comment. This operator called Laplacian, if we have a heat transfer in a spherical object, if we immerse a copper ball into a hot oil bath, then the temperature rise inside the object can also be analyzed based on this equation, but the operator can be represented in spherical coordinate. So this equation is sufficiently general for three-dimensional object in Cartesian, spherical, cylindrical objects. It can also be used in the analysis of diffusion. Now let's look at the simplest case. If we have a metal one-dimensional object with a length L, and this object is well wrapped, so there is no heat conduction across the boundary except the two ends. Then this equation this heat conduction inside the object can be analyzed by this equation. And we are going to use subscript XX to designate the second order derivative of u with respect to x. In order to solve this equation, we need three boundary conditions. Two are associated with the x because it's a second order with respect to x. So we have to integrate this two times. We need two boundary conditions. And on the left-hand side, it's a first order partial derivative of u with respect to time. So we need one initial condition. If we fix the two ends of the one-dimensional object at the zero temperature all the time, these are two sufficient boundary conditions. And we need an initial condition like we did for the string vibration problem. We leave the initial condition sufficiently general as a function of x. Then we are ready to solve the equation. Like we discussed earlier, we begin by a common assumption that the variables can be separated. So that means the solution can also be separated into two parts. Solution, because the variable, dependent variable, depends on two independent variables, x and t. We separate the solution into two parts. One involves factors of x, the other part involves factors of t. So we put this assumption into the original equation. We get this equation. Notice on the left-hand side, it's a first order partial derivative with respect to t. So this g dot represent first degree derivative, first order partial derivative. F is a factor involving x only. On the right, we have constant times f double prime. F double prime means second order partial derivative, actually ordinary derivative of f with respect to x times g. And then the next step is separating the variable for this equation. Remember, this is a rule we follow. The next step, we always separate the variables, leaving all the factors involving x on one side, leaving all the factors involving t on the other side. We usually leave the constant on the side with t. The reason is we are going to solve f first, and we don't want to carry this constant all the time. Then we are ready to solve. If we look at this equation, one side depends on x only. The left-hand side depends on temperature only. But this equation must satisfy a wide range of x and t. So we cannot just change x and make the other side the same. It's difficult. Only one condition, that is this side and the left-hand side equal to a common constant, k. We call k in the string vibration problem. We're going to do the same for this problem, assuming it equal to k. And then we can break it up into two equations like this. And the negative p squared is actually k. If we look at that equation, we get this equation, we realize because p is not a known value at this moment. So this second order ODE is an eigenvalue, eigenfunction problem. So we have to find the eigenfunction, that's the solution of the equation, and the eigenvalues along the way. We are not going to analyze all the three different cases like we did for the string vibration problem, because we have done so many cases in the chapter 11. We concluded that for k greater than 0 and k equal to 0, we have trivial solutions. We are not going to get useful solution for u. Therefore, only for negative k, we have solution. That's why we assume k equal to negative p squared. Then we have this equation. If we want to solve this problem, we need to find the two related boundary conditions based on the given boundary condition at the position x equal to 0, we have 0 temperature. So we put the assumption in F0, G of T. Here, this equal to 0. Then we look at the condition. The only condition for this is true, GT must not be 0. Because if GT is 0, U is going to be 0 all the time. All the time. Therefore, we have a trivial solution. So this boundary condition will give us F0 equal to 0. Similarly, at x equal to L, we can break the U into 2 parts. Then we can make the same argument. In order for this to be true, and still we are able to find the solution, the only condition is FL equal to 0. Then if we look at the solution, F, we have integrating this equation 5, we get a very general solution because the characteristic equation have imaginary roots. So we have this as the solution. Then if we use 2 boundary conditions to find the parameters, we found this eigenfunctions. Sine PL equal to 0, therefore the eigenvalue can be solved and pi equal to L, and can be any positive integers. If we assume B equal to 1, then we find the eigenfunctions. We select the eigenfunctions as sine m pi x over L. Since there are so many eigenfunctions, we give a subscript, designate the different n's. It's a collection of eigenfunctions. Then this actually complete the solution for F. Then we have to look at the G side. On the G side, the temperature side, the time side, the equation we saw earlier, this equation, at this moment, P is already known, so we can write this equation in this format. We assume all the coefficient is lumped, can be lumped into lambda n. And this is first order derivative of G. So we can write its a solution. We can integrate only once to get this exponential decay function. Notice lambda n is a positive constant. So that means the temperature will decay over time. There are infinite number of G sub n because n can vary. N can give different lambda value and different parameter. If we combine the Fn and Gn together, we get the solution U sub n in this format. Notice it involves a sine function of involving x, an exponential function of t on the right. The lambda is already stipulated. And then at this moment, we notice if we want to find Bn, we can use the initial condition. And if we use just only one u sub n, we are not able to find this Bn very easily. If we use only one function without summation, using only one element, at t equal to 0, this reduced to 1. This f can be arbitrarily given initial temperature distribution. And without this summation, we cannot find Bn that will satisfy this equation. Therefore, we look at the sum of all possible un for its solution. This is the final form of the solution. It involves the summation of all possible u sub n. Then this is what we obtain on the last slide. Put in there, then the coefficient is still unknown. So we use the initial condition, we get this expression. If we look at this expression, the right-hand side is the given initial condition. Bn is unknown. So what it means is we are asked to solve to find the Fourier sine coefficients from what we learned in chapter 11. The Fourier coefficient for this equation is this equation. So the solution of heat conduction equation, one-dimensional heat conduction equation, is a Fourier series representation, Fourier series representation with the coefficient obtained in this way. And then for many homework problems, we are asked to plug in F, so we get a coefficient, and we can see the temperature distribution by using this equation. Now, we have an interesting exercise here. This problem says if we have a copper, one-dimensional copper bar of a certain length, 80 centimeter long, and it's well insulated around it, then and we keep the temperature at the two ends 0, but initially it has a temperature distribution like this: 100 times sine pi x over 80. It's a sine function over this range. We are asked to answer the question, how long will it take the maximum temperature inside the object to drop to 50 degrees C? The parameters of the material are all given. The 3 important parameters for this problem are all given. The first thing I would like you to note is sine function oscillates between 0 and 1. So if we have a sine function times 100, that means the maximum value is 100 degrees C. And that also asks when the temperature will drop to 50 degrees C, to half of its value. We start by using the solution we obtained in the discussion earlier. This is the initial condition, 100 times sine pi x divided by 80. If we put this into the sine, putting this into the Fourier coefficients we discussed on the last slide, putting this here. Notice we have 100 times sine pi x over 80. What do you think we are going to have? The parameter 100 can be taken out. So we are integrating a product involving sine. Notice this is assumed to be sine nx over 80. And so it's just sine nx, pi x over 80 times another sine pi x over 80. The length is 80. So what's going to happen if we integrate this function with different eigenfunction in this group? N can vary from 1 to 2 to 3, etc. Remember, the collection of sine n pi x over L form and orthogonal set of function. So even we have so many possible products of this integrand, there is only one product that will cause the integral to be non-zero. Do you remember what the orthogonality tells us? We get a non-zero value only when we integrate a product of two identical functions. So only if we integrate two identical functions, we get non-zero values. So for this particular case, B1 is going to be 100, B2, B3 are going to be all 0. And here we just put in the material constant inside lambda. So we get a lambda value. And putting in this, we get a solution like this. And to answer the question, when the magnitude will drop to half of its value, we can simply say, use the solution we just got equal to 50. And solving this equation for t, we get a number. Take about 6.5 minutes for a long object, 80 centimeter long object, to reach half its value. Okay. Because heat can go away only from the two ends. Now let's look at the same problem in another way. If the initial condition change a little bit to 100 times sine 3 pi x over 80, we are asked to answer the same question. Notice the frequency of this sine function tripled. So that means there are more sine waves within the object. And then we also notice, because the frequency, the sine function increase, like we discussed earlier, if this function changed, only for this integral, the only non-zero integral corresponds the product of two similar sine functions. And for the example we just discussed, the two sine function must be identical, so we are talking about sine 3 pi x over L. Let's return to this example. Then we're going to have the solution, and to answer the same question, how the max, how long it's going to take the temperature drop to half of its original magnitude. It takes only very short time. Now we have a triangle shape of the initial condition. This is very similar to what we did for stream vibration problem. If the temperature distribution, initial temperature distribution inside the object is a triangle between 0 and a half L, the temperature rises. It's a linear function. Then temperature drop from x equal to half L to L. Then we are asked to find out how the temperature distribution look like at any position at any time. A very important skill, like I mentioned earlier, is to be able to sketch the function, to understand how it looked like initially. And I would use MathCAD to illustrate the solution of the same problem. But if we don't have access to MathCAD, we can manually solve the problem. This is the Fourier sine coefficient. We have to break the integral into two parts. One part from x equal to x from 0 to half L. The other part from half L to L. We have to integrate all this. Integration by parts will lead to this solution. From here to here, it's going to take some time. And if we look at it, this solution, if you can use any software, please. If you have MATLAB, if you have Mathematica, by all means, please use the software to sketch it. You can tell this figure represents the initial temperature profile. Then when time goes by, you see the temperature start to drop because the two ends are kept at 0. Temperature keep dropping until it flats out. This is different times. And there are another type of problem. If the two ends of the one-dimensional object are well insulated rather than kept at the 0 temperature, how do we get the solution? Do we really have to derive the equation start from scratch? I believe I leave the detail to you as a homework, but here we have a sketch of the solution. Where is the breaking point of what we went through? Is something to think about it. If the two ends are well insulated, that means the two ends, the heat flux is 0. Heat flux is the derivative of temperature with respect to x. So no heat transfer. Okay, so this boundary condition means at x equal to 0, partial derivative of u with respect to x equal to 0. At x equal to L, partial derivative of u with respect to x also equal to 0. So how do we solve the problem? By using separation of variable. Where is the breaking point from the solution for last analysis, for the last example? Do we have to go from the beginning? We know the boundary conditions are different. We can leave the initial condition sufficiently general. We can still use the same assumption. We can still get a set of two ordinary differential equations. So this we can start from here. Our analysis can start from here, and even the solution can be represented in this way. Then the boundary condition have to be changed. So we have to use the derivative to analyze this problem. So instead of getting sine function as the eigen functions, we are going to get a cosine function. That's what's going to happen for the well-insulated object. Let's go down to this problem we are talking about. So the initial condition is going to be changed. The boundary conditions are going to be changed to this derivative is going to be 0. This derivative is going to be 0. Then we take the derivative of this function. We can start from the general solution for f, then apply the two boundary conditions we just talked about. We get these two derivatives, then we can find the final answer look like this. For each un, we get cosine function. And so the final form of the solution involving all possible u sub n look like this for well-insulated n. Now we can apply the given initial condition, arbitrary given initial temperature distribution like this. then we can realize since f is known, a sub n is unknown, this is a problem of Fourier series representation of a given function of f, and the an can be represented in this format. So remember, this is an even representation. It involves only cosine functions. Now, if we would like to solve the problem involving triangle initial temperature distribution problem we discussed earlier, then we can plug in f and find a n and an just like this. Okay, so I believe I assigned 2 problems associated with this type of problem in the homework. Please tackle these problems. And before I switch to the study guide, let me emphasize again, we're probably going to run out of time this semester. For a 2-dimensional heat transfer problem, we're going to have this type of equation. So this is still a second-order PDE, linear second-order PDE. And we can use separation of variable to solve it. But we're not going to discuss this any further. Now let me switch to the study guide so we can see more examples. Starting from page 134 of the study guide. This slide summarizes what we have been talking about in this lecture. These are the governing equations, PDE, 2-boundary condition, and the given initial condition, the very general, and the separation of variables yield solution like this with coefficients b sub n like this, and the parameter lambda n is defined as this. And earlier we have solved this type of problem. And in mass camp, we can put a bn in the integral by hand. So you have my long solution by hand. Integration by parts will stepwisely leads you to the answer, but please do this once so you can figure out the potential problem in the solution. For example, if we encounter cosine n pi over 2, we may have trouble to assign a value. Cosine n pi over 2 can be positive 1, negative 1, or 0. So I actually break it up into 3 parts. Notice in the subsequent discussion, every time we have difficulty like this, we break it up, just assume odd number, even number, and another group of even number. Okay, break into 2 or 3 parts, we can eventually get numbers. So this takes a while to get it, but I strongly urge you to go through at least one problem by hand by yourself because this kind of skill is going to be needed. Then we can see I let Mascad to do the integration for us. I got this answer. I checked this is what I got by hand. Okay, this is the right sequence. You want to make sure if you learn it well. So Mascad is a useful tool. So I sketch it, initial distribution of temperature, put a parameter in. I represent this given function by using the absolute sign. This is another way of doing this. You can break it into two segments, or you can use unit step function. There are many different methods to represent this. Then we use what we obtain here as B sub n, Bn. Then this is the solution, 20 term sum of the temperature distribution. I essentially reproduce what I also want to produce. You can tell the temperature drop essentially to 0 over time. Okay. Now, this is a summary of what we discussed for the well-insulated end. So the governing equation is the same for PDE. This is for heat energy balance of the inside the object. The two boundary conditions are slightly different in terms of their partial derivatives at the two different points. The initial condition can be left sufficiently general. I believe one of the homework problems also wants you to generate this. I already sketched it. This is the general solution. This is the Fourier cosine coefficients. And if we have this initial temperature distribution like this, again, I get the Fourier coefficients like this, the initial temperature distribution, and then this is the initial temperature distribution over time. In the middle of the object, the temperature will drop. Near the two ends, temperature will rise and eventually reach a horizontal temperature distribution. Now, the important question is, can you believe this is what we're going to have? The answer is yes, because the heat inside the object doesn't go anywhere. It has to stay inside the object. So it doesn't go out, so it has to stay and cause the low temperature to rise. Eventually, it reaches the same temperature within the object. Okay, so this is different from the last example where the two ends are kept at 0 degree. This is animation. I'm not going to talk about it. Now, finally, this is for advanced student. This is also in my study guide. This has been solved. This is just reproduce what I talked about earlier. If we have 2n at the 0 degree, and this is steady state temperature distribution, I demonstrate temperature distribution is linear. Now, the important thing is, student may ask if we can solve problem with a homogeneous boundary condition. Remember, the word homogeneous means it involves the variable, the dependent variable only in the boundary condition. It's called homogeneous boundary condition. If we have a constant here, then it's considered non-homogeneous boundary condition. Can we still solve this problem? Because student may ask, if we can solve only the problem involve 2 0 temperature at the 2n, what's the use? So this example illustrates, yes, indeed, we can solve the problem. We can solve the non-homogeneous boundary condition problem. At the 2n, we kept at the 2 arbitrary temperature. And if the initial condition is a horizontal line F, the temperature will decay to this straight line. And here is my solution. I assume the temperature will decay to this linear line like this. This is based on my intuition, which will be demonstrated to be true. The key to solving this problem is by assuming the solution to this problem, W, is the sum of a unresolved problem plus Vx. If we subtract the steady state temperature distribution from the problem we have, then we shall be able to find y, the difference. This difference is 1. We can solve for y like this. Because V is already known. Our goal is to find W, but Y is something we can find because we can find the boundary condition associated with Y are going to be homogeneous by using this substitution. It's interesting to know, once I put in the assumption, equation 15 is the key. But it seemed to be justifiable from the sketch. We postulate we shall be able to get, indeed, when I put in to the PDE, I got this portion, and so the differential equation doesn't change, remember, the same. The boundary condition remains as a homogeneous boundary condition. It becomes 0 for y at the 2n. Very, very interesting. And then if we look at this PDE and with this 2 boundary condition, we can solve this PDE very easily. by, this is what we get for U actually, same as for U. But the coefficients is going to be different because the initial condition is different, but we can easily get. Then finally, if we want to get W, we only need to use our assumption. W is, remember, W equal to Y plus V. We just add, this is a Y, this is a V. And inside the solution, Bn star look like this. So this complete my talk on the one-dimensional heat transfer problem. I wish you good luck. I hope you had a good time this semester. Good luck to your final exam. Remain healthy for the summer. I look forward to meet you again in the fall if you're going to stay at the Ole Miss. Good to have you.